just a quick recap for what happened in the past 3 years. It turns out we have been doing this for 3 years already. Since today, we have a telescope. Since today, a lot of these programs sprung up, and Grant has this nice review article back in 2022, which now this figure is now 3 years too old, or 2 years too old. So I wish we can keep updating this, and then we have an overview of what has been done. But then the universe never stopped throwing us problem, puzzles, questions. Too many galaxies, who have guessed that? And the luminosity function keeps going, not just to fainter magnitude, but also keep going to redshift 15, redshift 17, redshift 25, redshift 30. So a lot of discovery, and what I do is quite complement to that. What I really care about is interpretation. How do we understand these galaxies, the physics that drives them? How do they form so quickly? And I do SAM. We rely on the assumption that we know how halo formed. And just to quickly set the stage, in order to do that, we need merger trees. We need to know how halo formed. And there are no simulations out there that can provide us that information at redshift 10 and above, because there are so few snapshots stored. And it's not a bad thing for them, because these simulations are not designed to capture how halo formed in the early universe. So I came up with this set of GUREFT simulation. It stands for Gadget at Ultra High Redshift with Extra Fine Time Steps, and the name says it all. These are a suite of n-body simulations that is done at the ultra high redshift, and we store snapshots at extremely high cadence. So that gives us the basis for the merger trees that we need. Another thing is, halos at these early times are both rarer and lower mass than their lower redshift counterparts. So to simulate these halos at early times, the boxes will have to be bigger and higher resolution, which we can easily break the bank. I don't want to do a 6.3 trillion particle simulation with 10 to the 4th solar mass resolution. That's just not feasible. It's just too much to process. So instead of doing that, we ran a suite of 4 boxes that gradually step up in volume and down in resolution. The idea is to capture the halo mass ranges that are relevant at these times, but using different boxes. It's just tier setup. With these 2 combination graphs, just provide these great merger trees that we can work with, and you'll hear more how we make use of these merger trees in the rest of this talk and also in Rachel's talk. Okay, quick pause, change of topic. So there are several quests that that we has been trying to go answer these questions and to make use of GUREFT. So one thing is, do redshift 25 galaxies break the universe? We have seen this before. Redshift 12 galaxies, we saw a bunch of them. The universe is broken. Turns out it's not. So we preemptively look at these and try to ask ourselves the question, can we make these galaxies? So you heard this from Pablo's talk. There are a lot of them, and they lie well above some of the theory predictions at this redshift range. And then there are also luminosity function estimates, and here are some of the cutouts. So many of those are still candidates, but we try to answer the question, if they are real, what are the implications? So GUREFT is amazing in several ways. First, we have simulated halo mass functions. They go all the way out to redshift 30. They are not extrapolated. There are in the past simulations that go up to redshift 10, redshift 15, and then halo mass functions being fitted, and then the fitting functions get extrapolated. The problem is the further back you go in redshift, the more off they are. So these are not extrapolated. We actually have these halos from the boxes. We have to stitch the boxes together, but the halos are in the simulation. So we have halo mass function out to redshift 30. We can also back out the halo mass accretion rate. And this is even harder to do because you can resolve a halo with just 100 particles. That's fine. But to measure the accretion rate, you need even higher resolution. Otherwise, a particle is 1% of the halo mass, which is a huge jump. So you need both. Now with that, we can come up with this toy model trying to ask ourselves if star formation rate traces how quickly halo accretion gets. And the star formation rate is converted to luminosity through some simple conversion factor. Can we make those 30 galaxies? Or in other words, does it break the universe? Is there enough matter in the universe to make those galaxies that early on? So what we do here is look at a few redshift snapshots. These are the observational constraints shown in the ray data points, redshift 12, 14, 17, and 25. And the blue line there shows the absolute max scenario, where we have epsilon star, the conversion efficiency, equal 1. So all the gas get turned into stars, absolute max. just putting a ceiling there, not to say it's physical. And you can see that at redshift 25, these constraints, and this solid line is redshift 25, well, we can actually make them, given the amount of baronic matter budget there. It's just that, well, you have to figure out the exact physical processes, how did that happen. But at redshift 30, there's still not too crazy. There's still this little range that redshift 30 and redshift 20 spans. Now, someone would probably just come up and challenge me, 100% conversion rate, in what universe is that physical? It turns out we don't even need that. So what we did with Kartik is that we did a little MCMC fit by holding the conversion efficiency epsilon star as a free parameter. And then we let it change as a function of redshift and halo mass. And we ask ourselves empirically, what does this efficiency has to be in order for us to reproduce these observational constraints? It turns out nothing too crazy. Too bad I covered this up, but this is around 20% at redshift 12. And even at redshift 17, to reproduce these observational constraints, the brightest point, all we need is about 60% of conversion efficiency, which you'll see in the ratios talk in a bit. It's not too absolutely physically crazy. We can still do that. And this is what we're going to back out at redshift 25, which is still not like unreasonable. And now here, all these upper limits are our upper limits. So we didn't force the model to match that. So this is just to demonstrate that graph can be really helpful in the redshift 30 space, because now we have a halo population that we can look at and put some ground on making these type of predictions. I'm going to put a little pause here. I'm going to completely change the topic. So I've been working with SAM for my whole career, which is pretty short, but the Santa Cruz SAM, which is born here, and this is my flow chart for how it works. So some of my understanding is just it's a list of carefully curated physical processes that we put together, so that at the end product it well reproduced the galaxy evolution across a wide range of redshift. And here are the luminosity function that it produces from redshift 8 to 17 compared to some of these latest JWST observations. Now, you've seen this probably a few times in the past, because I show luminosity function in all my talks. And I often get asked questions like, how does galaxy actually evolve over time? Not talking about as a population, that's something we see all the time. But what is the progenitor of a redshift 8 galaxy here look like at redshift 15? Can you point it out somewhere here? Hard to do that in your head. So I get asked like that pretty much constantly throughout my career as well. So this time I bit the bullet and actually do it. So these are plots I tried to make with the full star formation history backing out from the Santa Cruz SAM. Same model you saw in the previous slide, same model, same result you see over the years, but a different viewing angle. So now we have galaxies getting color-coded by their final mass or terminal stellar mass at redshift 6. And these are their star formation or stellar mass assembly history tracked backward in time, keeping the same color. And you can see it's really messy. Not always the most massive galaxy get the most massive progenitor. I mean, maybe one of them out here, but down here is pretty mixed. So to make things a little more digestible, I try to organize things a little bit. So in this panel, I bin galaxies by their terminal stellar mass at redshift 6. And I look at the stellar mass growth history for these galaxies that are hopefully comparable in mass at redshift 6, and try to look backward in time and see what their star formation history are like. So one thing I do here, these are 10 to 6 solar mass, and then a step all the way out to 10 to 8 solar mass at redshift 6. And what I also trying to measure here is two quantities, one called T50. The time it takes for these galaxies to form 50% of their stars, and then T90, the time it takes to form 90% of their stars, or just most of their stars. And then I drop that number down here into this histogram. And now we can see how the distribution of T50 of these 10 to the 6 solar mass galaxies, how long do these galaxies form their stars? And I made a mistake. I said redshift 6, but actually this ends at redshift 12. And it was selected here for redshift 12 for a reason. Well, for a long time we thought that galaxies take 100 million years, 200 million years to form their stars, and these short time scales are okay to be treated as a single band. It turns out that for these redshift 12 galaxies, stars are formed really rapidly. And here we have a T50 median of about 30 to 40 years for these redshift-12 galaxies. So all these galaxies are forming half of their stars, the most recent half of their stars within the past tens of mega years, which is very fast. Almost every galaxy can be classified as a starburst galaxy by redshift-6 standard. So we actually need to resolve the single million year stellar mass bins when we do the SED fitting. And that ties back to the very depressing talk I gave last year. You probably don't remember anymore. But what is really important is going down this rabbit hole. Now we can measure T50 for all our SAM galaxies, and I can compile a heat chart like a heat map like this. So we have T50 for a redshift 15 galaxy that goes down to just 20 million years. It takes 20 million years for these galaxies to form half their stars. But then these numbers go up as we go down to lower redshift. These same mass galaxies at much lower redshift can form stars. Well, it will take over 150 million years to form half their stars. It's just these galaxies of similar masses, perhaps similar luminosity, well, slightly fainter for the lower redshift ones, can take completely different star formation course. We kind of know this in our head, but we have never seen this be put on a plot. So this is like one example I can do. So we have a redshift 6 galaxy. This time I said it right, and a galaxy ending at 10 to 10 at redshift 6. Now I can grab all the galaxies from our simulation with an evolutionary track that will lead to these end stellar mass, which is quite interesting. And here's the median, there's a spread. You can see there's some late grower that grow really quickly, and there are also some slow grower that grow fast early on, but then kind of slow down in star formation. And then I can also back out how quickly their halo mass grow, which is very interesting. So now I can tell you, if you give me a galaxy at redshift 6 with 10 to 10 solar mass, then its progenitor could be a 10 to 9 galaxy at somewhere between somewhere redshift 7.5, or it can be a tiny 10 to 6 galaxy at redshift 14, that kind of thing. So this, we're trying to write this up, but this is kind of like a little demo what we can do now with this new angle of viewing SAM simulated galaxies. Another thing is I just show you how quickly a halo can grow, and also how quickly this galaxy can form stars. So now if I divide this two, well, this is one way we can define the star formation efficiency right here, actually, stellar mass versus halo mass multiplied by the Brownian fraction. So now I have galaxies also binned by their redshift 6 stellar mass. And these are their evolution of the star formation efficiency over time. For galaxies in the same halo, not choppy snapshots that we stitch together in hindsight. So what I see now here, very preliminary, is that apparently these more massive galaxies forming more massive halos just constantly having higher star formation efficiency than their lower mass counterparts across the whole cosmic history. And it's something I still have to digest a little more, but having a plot in front of me that answers some of the questions that have been asked constantly over the past decade, apparently, it's quite interesting. So back to this plot that I kind of showed before. The big fuzz, why do I have to do all of these work to figure out the star formation history, is because in the past we've binned the star formation history from the SAM with these 10 million year bins. So we bin them, and then we assign a stellar SED for stellar population in each bin. So in the past we do these 10 million year bins, we group all of these stars into a single bin, and then we assign them a stellar populations SED with the median redshift, median age, which is 5 million years. And these really underestimate the luminosity of these galaxies that we compute by quite a lot, by maybe 2 magnitudes. So if we do that correctly, it brings our luminosity function to the right by that amount, and we actually can reproduce the observational constraints out to redshift 12 without needing to change the model. So, which is quite nice. But of course, out at redshift 17, we still don't reproduce these observed data points. And of course, Rachel will tell you how we get around that. So here's a quick summary. There are these two things. Redshift 25 galaxies do not break the universe. There are halos. There are plenty of baryonic matter out there. How they form stars quickly is up for debate. What I want to say one more thing is we don't actually need 100% star formation efficiency, and we don't need crazy number to explain those redshift 30 candidates. We'll probably just throw in a reasonable amount of boost from top-heavy IMF, and also some scatter from bursty star formation at these times. But we can still make Redshift 30 galaxies quite comfortably, not easily, but within the modeling framework. And here is, we have STEM predicted star formation histories, and this is a new way for us to make use of SAM predictions and look at how galaxies can grow their stellar mass over time and connect the progenitors to their descendants using the simulations. All right, I'm going to stop here. Thank you.
Yeah, well on time, so questions?
So you use very high resolution simulations, cadence, growth with information payload. You would use many redshift-based algorithms to do this, and there have been numerous papers that sort of predicted how the mass things, how they grow over time. Did your simulations reveal any inconsistencies between those? Anything new that you learned, or it was sort of all consistent with?
There's something new we learned. So there's a not side project, but some project based on this graph simulation. We had a pre-doc at the CCA before, and now he's a postdoc at Sierra, who looked at these halo, how they grow, how they merge, and then use machine learning to back them out. And then so we now have a sort of extended pressure structure-based algorithm, well, extended pressure structure-like algorithm that grow merger trees, but based on the things we learned from these graph boxes. What we learned is there is some dependence on the environments that's not captured by extended pressure structure. Something I kind of noticed now, even with graph, is that some of the halos we see at, well, galaxies we see at Redshift 20, living in halos, they're probably not halos forming in a cosmic average environment. They're probably in this overdense region, but the whole suite of graph boxes are done in cosmic average density. So one thing I didn't get to talk about is GUREFT-II, which will actually do a more targeted zoom in to go after the overdense, underdense region. But there is some dependency on these cosmic environments that EPS is just not capturing or not fully representing.
Next one.
Hi, Aaron. Very impressive. So in the ultra-sim empirical paper, I was wondering about, so how do you compute the UV luminosity for galaxies? I mean, are you using a constant conversion between UV luminosity and the star formation rate?
Yes.
Or?
So here we have the star formation rate is converted with a simple conversion factor, but then this KUV is taken out of modality case in 2014, just a fixed number that convert over. But the bottom line is we check this number against the SAM predicted KUV, and they're not that different.
Right.
They might have gotten it right for some bizarre reason.
Yeah. And the other question is, are you assuming that these galaxies are transparent? I mean, in other words, all the star formation rate is in UV?
In UV? Yeah, that's the assumption, right? So, well, this is not the assumption, but this is folded into KUV, right? This is just the number that convert the amount of star formation rate into LUV, assuming that all of those contributed.
Okay, thank you.
Probably time for one more question. Yeah, okay, yes. Yep, go for it. A microphone might get to you eventually.
The mic's coming.
It's on its way. There it goes. There you are. Right.
I'm just curious in these ultra-Z galaxies, what the baryon fraction is in the halo that you would predict.
Baryon fraction?
I mean, are they feedback free enough that we're at the cosmic ratio, as opposed to, you know, modern day dwarf galaxies where very few of the baryons are still in the halo?
I suppose this number is fixed coming from cosmology. It's just the amount of baryon that, well, so there's amount of gas that come in with cosmological accretion, and then we use that to scale to the amount of hot gas in that is coming in.
But you don't have feedback?
The next plot? This one? So this is the efficiency of how many percent of the hot gas get converted into stars.
100%.
Well,
Okay.
the blue line assumes 100%, but this is what we actually need to reproduce these constraints. So this is 20% here, 40%. So
I see.
in a very rare circumstance, we now need 60% peak for Redshift 17 for this bright stuff. But that's, yeah.
Okay, thank Aaron again.
You gonna plug in?
I should wave 5 fingers when you've got 5
think
fingers
they-
to go. And shoot me with the microphone too.
They want you to zoom.
It's 15 plus 5, yes. Yeah. That's the plan, at least.
Is that okay?